Hello, this is John Noguera from SigmaXL. I will be your presenter. The topic for our webinar is how to deal with non-normal data in process improvement projects. Our agenda for today, dealing with non-normal data, it's somewhat of a controversial topic. What I want to do is I lay out a groundwork for dealing with non-normal data and talk about situations where the tools are robust and situations where the tools are not so robust against non-normal data. So first we'll look at the SigmaXL tools to detect non-normal data, and there are both graphical tools and statistical normality tests. And then things to consider when you're dealing with non-normal data. Do you have outliers, or do you actually have inherently non-normal data? Do you have a bimodal distribution? Do you have a problem with your measurement system? We'll look at those issues. And then I want to talk about the Central Limit Theorem and sample size guidelines in terms of how well is a hypothesis test going to work if you have, let's say, slightly skewed data. And then we'll talk about the SigmaXL tools to deal with non-normal data, and those are transformations and distribution fitting and nonparametric tests. Now, for that, what I'm going to do is I'll go through the SigmaXL workbook, and we'll look at the examples that are in the workbook. I like to do that because that way you have a document that you can go back to and refer. The SigmaXL manual, if you go to Programs, SigmaXL, and then the SigmaXL guide, if you've installed SigmaXL, then you have the workbook. Okay, so let's begin now, and graphical tools. Okay, so I want to talk about detecting non-normal data. Histogram. All right, well, a histogram can be used to detect skewness, bimodal distribution, outliers, and even truncation. These are all different reasons why you may have non-normal data, and it's important to use the graphical tools to look at your data, because depending on the reason for the non-normality is going to take you in different directions in terms of how you deal with that non-normality. And then and we'll get into that in just a bit. Boxplot is useful for detecting outliers. Control chart or a run chart can be used to detect trends and outliers. And then a normal probability plot, which is really, I think, the key tool here, helping you to separate outliers and inherently non-normal data. All right, so we'll look at some examples of that in just a bit. And then you have your normality tests, and the most important one is the Anderson-Darling. It's the most powerful non-normal test, and so the way you interpret that is that first of all, the null hypothesis is that the data are normal. So if the p-value is low, you reject that null hypothesis. So if the p is less than 0.05 and SigmaXL will flag it in red, that means the data are not normal. Okay? And if it is greater than or equal to 0.05, we'll assume that it's normal. You never prove the data to be normal, but we'll just assume the data to be normal. And then, of course, this is always used in conjunction with the graphical tools. And then other normality tests that are in the descriptive statistics include skewness and kurtosis. And the same guideline applies. A p-value of less than 0.05 will indicate significant skewness, and less than 0.05 will indicate significant kurtosis. Now, skewness is the direction of the tail. That is a long tail. And kurtosis is whether you have a peaked distribution or a flat distribution. So any departure from a normal bell shape will come up as kurtosis if it's either peaked or flat. All right, so these are the tools that we're going to be looking at to help us to simply detect that we have non-normal data, and then most importantly, what's triggering the non-normality, not just whether or not we're dealing with non-normal data, but what might be actually causing that. And I want to start with the question of outliers. Outliers, it's possible that you can have outliers, and that will actually trigger your data to appear to be non-normal. I have an example here. Now, this is a normal probability plot, and in the normal probability plot, if the data fall on a straight line, and it's always an approximate straight line, then you can assume that distribution to be normal. However, notice that there is one data point out here that's kind of far away from the rest, and that data point is an outlier. I also I'm showing that up here with the box plot, the same thing. The dark circle indicates an extreme outlier with the box plot, and the light circles indicate potential outliers. Now, the box plot is very sensitive, so keep that in mind. A potential outlier is not necessarily an actual outlier, but something that you want to have a closer look at. But definitely anything that is a solid circle with the box plot is a large outlier or an extreme outlier. Now, what's interesting here is that with the outlier in the data, you can see that we fail the Anderson-Darling normality tests, 0.025. If, however, I remove the outlier, we see that the data is in fact normally distributed. So this is an example where the data show as not normal, but the reason for that is because of a single outlier. We remove the outlier to do the normality test, but I want to caution you on deletion of data. I think that's something that you want to be very careful of. You don't want to just simply scrub your data to remove outliers. You need to deal with the special causes. You need to get to the root causes, find out what caused that outlier, and address it. But on the other hand, in terms of doing statistical tests of hypothesis or wanting to make sure that you have correct assessment of mean and standard deviation, then the reason that you're dealing with non-normal data is because of this outlier, and it's not really appropriate to try to transform that data. We'll talk about transformation, or trying to do a distribution fit. You may want to use nonparametric tests in this case. All right, so that would be one option that you could use are the nonparametric tests if you're doing hypothesis testing. But most importantly is that you try to understand why you have the outlier. Outliers are valuable in the sense that we can learn lessons. For example, DuPont invented Kevlar as the result of investigating an outlier. And so there's actual discovery in understanding your outliers. They're unusual data points. And so you want to learn more, study your outliers, try to understand the root causes, and then address those. If, however, the outlier is simply data entry, a known data entry error, then obviously in that case it's okay to delete the outlier. All right, so I just say that with caution. I'm removing it only to do the normality test, and in this case we determine that yes, the bulk of the data is normally distributed and we're just dealing with an outlier. So it's not appropriate in this case to trying to go transforming this data. So that's the question of outliers. Now, what about inherently non-normal data? Well, here in this normal probability plot, remember what I said, a normal probability plot, we expect the data to fall in a straight line. Well, clearly here we don't have a straight line. We have a strong curvature in the data. And this is actually an exponential distribution. And so the normal probability plot shows that strong curve. And with that, you can conclude that we have inherently non-normal data. You're not just dealing with a single data point. The entire data set is following a distribution that's different from a normal distribution. And in this case, it would be perfectly appropriate to look at transformations like a logarithmic transformation or some type of distribution fitting. Okay, so that's the question of outliers versus inherently non-normal data. Now, another thing that you need to think about and consider is our bimodal distribution. And a histogram is really the best tool to help you to visualize a bimodal distribution. And you see the two peaks. Of course, you can have more than two peaks, but typically this is what you might be looking at. And here's another situation where it would be inappropriate to trying to transform this data. What you have is simply there's an X factor. There's something that's going on in the process that's causing the process to change. It could be day shift, night shift, person to person, different raw materials, location to location. Something is going on that is an X factor or a group category variable. And the best approach to deal with that is really is to stratify your data. So use the group category variable, or at least try different group category variables, and then use the two-sample t-test to understand what is the significant X factor. And then you want to control that X factor. You want to put standard operating procedures in place to try to correct or identify this and essentially get this process looking as a unimodal distribution. All right, but again, to recap, it would really not be appropriate to try to transform the data. The best approach here is to try to understand that X factor. The next issue that we have is chunky data. And chunky data is a situation where you have problems with measurement discrimination. And the best way to see that is with a normal probability plot. And what you're looking at, these vertical lines or vertical stacks of data. And when you see that, that's telling you that your measurement system is not able to resolve the values between, in this case, I have integer values. What I did was I took a normal distribution and then I used rounding and to come up with distinct values. And while it actually follows a normal distribution, you can see the Anderson-Darling test says that this is not normally distributed. But what's interesting is that in terms of skewness and kurtosis, we fail to reject. So in other words, we don't have a problem with skewness and we don't have a problem with kurtosis, yet the data is still not normal. And really the only solution to this is to try to improve the measurement system. So here's a situation where if you have this chunkiness in your data, Anderson-Darling is going to tell you it's not normal. So what do? Well, if you cannot improve the measurement system, you may just have to go with the data as is, but understanding that the p-values are going to be suspect. All right, so these are kind of upfront issues. I didn't actually cover truncation, but that truncation is a situation where you see it in manufacturing where let's say you're testing parts and then you have a hard limit and you separate out. So essentially you ship the good product and reject the bad product. And in that case, if you look at a distribution, it might be normal, but it's a truncated normal. You might be able to try to represent that with some more advanced distributions, like a beta distribution, but the ideal is to get the entire population of data. That's really ideally what you want, is to go back to the data before it was filtered so that you're back to a normal distribution. Now, I want to talk about the Central Limit Theorem. The distribution of averages tends to be normal. What that means is that if you're testing averages, if you're comparing averages, then the Central Limit Theorem does apply. So whether it's a one-sample t-test, a two-sample t-test, an analysis of variance, or X-bar chart if you have a control chart, or even a design of experiments where you have replications and you're comparing average of lows to average of highs. So in all these cases, there's averaging that's going on. And when you're comparing averages, then you have this Central Limit Theorem that kicks in that says averages tend to be normal. Now, if you're dealing with individual observations, like an individual's control chart, Central Limit Theorem does not apply. Okay, so this only applies to tests that involve means, the use of means. What does this imply? Well, if I'm doing a process capability study, or if I'm creating an individual's control chart, I need a normal distribution. This is, of course, where the controversy kicks in, and recently there have been interesting articles on Quality Digest and debating to what extent is the individual's control chart robust to non-normality, but I'm in the camp that says, well, if the data are not normally distributed, the tools are there to help you to deal with that, and so therefore transformation is appropriate. So if you're doing a process capability study, CP/CPK, or if you're running an individual's control chart, then you have non-normal data, inherently non-normal data, not just unstable data, but data like the exponential distribution, or if you look at the normal probability plot, it's showing a strong curve, then you really should apply transformations in that case. However, if you are dealing with averages, then the question comes down to, well, to what extent is the data non-normal? And what the important measure that comes out here actually is skewness. And I did simulation studies, and I came up with this rule of thumb. It's just an approximate rule of thumb, but it actually works quite well. And that says that in order for Central Limit Theorem to work, or to be, let's say, good enough, or your data to be close enough to be normal for the hypothesis test to still work reasonably well, you need a minimum sample size of 50 times skewness squared. So if you have mild skewness, and by mild, I'm saying a skewness of less than or equal to 0.5, then you need a minimum sample size of 30. So that's your typical guideline says you want to have minimum sample size of 30 anyways, and if you're doing a hypothesis test and you have just slightly non-normal data, then you're fine. Just go ahead and everything is going to work okay. Central Limit Theorem will work for you. If you have moderate skewness, and I define that as up to a value of 1.0, then you're going to need 50. Now, if you have strong skewness, then you really need to get into very large sample sizes. In this case, you'd need at least 200 sample size for Central Limit Theorem to be able to deal with this strong skewness. So this would apply to, again, hypothesis testing on the mean and X-bar control charts. Now, if your sample size is too small and it's just not practical to get a larger sample size, then you will have to use the nonparametric tools to do the hypothesis testing. Okay, so now this leads us to the SigmaXL tools to deal with non-normal data. I've been mentioning transformations and distribution fitting, so we're going to have a look at that in more detail. And where in SigmaXL do you get that? Well, the capability combination report, individuals non-normal. We also have a distribution fitting tool, and we also have an individuals non-normal control chart. In this webinar, I'm going to just look at the capability combination report because it actually already includes the control chart. Very popular technique is the Box-Cox transformation. What's nice about the Box-Cox transformation, it's raised to the power of. So if I can take a logarithm or a square root and I transform the data, and now it's like cycle time. Often if you take the logarithm of the cycle time, then the logarithm of the data is normally distributed. You see that a lot. And what's nice about that is that it's quite straightforward. It's not a complicated transformation. Other software tools, if you were trying to use a Box-Cox transformation and you had negative numbers, then the Box-Cox transformation would fail because you're trying to take the logarithm of negative values. What we have in SigmaXL is something called a threshold, and a threshold actually adds a shift factor to the data so that it'll do that first, automatically basically slide your numbers over and then solve for the transformation. So that's a nice feature that we have that's not commonly in other software packages. Now Johnson, on the other hand, is very powerful, and it's a very powerful transformation, but it's also quite a complex transformation. And there's actually 3 or 4 parameters involved. It's not just like a lambda raised to the power of, but it's a much more complicated transformation. However, it's also very, very powerful. So if Box-Cox doesn't work, typically Johnson will work. All right, so that's kind of the order that you probably want to follow. And in the majority of cases, Box-Cox will be sufficient. But if you have, difficult data, then often Johnson will work. Again, please keep in mind, we're not talking about measurement discrimination issues. We're not talking about just, outliers or bimodal. We're talking about inherently non-normal data. I would say that pretty well any unimodal distribution, any unimodal non-normal distribution can be transformed to normality using the Johnson transformation. In SigmaXL, we support a variety of distributions. So this is the distribution fitting. So distributions supported, we have the half normal, the log normal, the exponential, Weibull, beta, gamma, and so on. Reliability work is based on a Weibull distribution, lifetime data, whereas for the most part, you're not going to know whether you should use a gamma distribution or a log logistic distribution. So what we have is we have something called an automatic best fit, and it will go through and it will attempt all of the various distributions and transformations and essentially come back and give you what the software selects as being the automatic best fit, and then you can look at the Anderson-Darling p-value and say, is this working for me? And then you go ahead and use that. Now, what I'm going to do is I'm going to use the workbook example, and I'm on page 125 in the workbook, just so you know. Go to SigmaXL, and the data set that I'm going to use is non-normal cycle time. So one of the questions here is some examples where non-normal data would pop up. Cycle time is often data that is not normally distributed. Customer satisfaction tends to be not normally distributed. You'll have more 4s and 5s and fewer 3s, 2s, and 1s. If you have situations where you have a hard limit, like the numbers cannot go below 0, often then you see this sharp drop off on the left side and then a long tail, which is what we're going to look at here with the cycle time. What I have here is cycle time. This is an example of non-normal data. So let's begin with a view of a graphical view. And so what I'm going to do is look at histograms and descriptive statistics. And we'll look at the cycle time. And so as you can see, you have this long tail, and the normality test fails. So the p-value is less than 0.05. And so we have the data are not normal. And I also want to run the descriptive statistics for you so that you can get the skewness and the kurtosis values. And as you can see here, the skewness is a large positive value. So the skew is the long tail to the right. Okay, so when you have a long tail to the right, that's a positive skew. We also have significant skewness and significant kurtosis. So this is definitely not normal data. And let me just do a normal probability plot so that we can have a look at that and make sure we're not just dealing with a single outlier. And as you can see here, you have that curvature in the data indicating that this is a non-normal distribution, inherently non-normal distribution. With that, what I want to do is I want to take the next step, which is you're trying to improve this process. You want to establish a baseline. And one of the things you want to do is run a process capability study. So when you run a process capability study, one of the assumptions is that the data is normal. So I just go into process capability. Let me do the capability combination report and do cycle time. The upper spec limit in this case is 1,000. We'll go ahead and run that. We saw the histogram. We saw the normal probability plot. if we look at the control charts, it looks like this is a process that is out of control. Also, we see that, in fact, we have, the PP is very low. So 0.1, you want to have a PPK obviously higher than 1, preferably, more than 1.3. But obviously, this is a case where the process is not capable. It looks like it's an unstable and not capable process. So you want to report to management what the current process capability is, what the baseline is. But notice something here. In this process capability report, you have two things. You have expected performance and you have actual performance. The expected performance is the expected performance assuming a normal distribution. In this case, we're predicting 40% to be outside of the spec limit. What's interesting, however, is that the actual performance is 10%. So there's quite a discrepancy. The fact that the data are not normal means that we cannot trust this expected performance number. It's assuming a normal distribution. So what do we do about that? If I had a large sample size, say 500 or more, then the actual performance could be used. So you can actually go to the discrete number and report that as an assessment of your performance. But in small sample size case, you really can't do that. This is not going to be a reliable indicator of performance. So this is a situation where I really do need to transform the data and then do a process capability on the transformed data. So with that, we'll do the process capability, non-normal, and then capability combination report. We'll select cycle time, and the upper specification limit was 1,000. And we have a variety of techniques. I mentioned Box, Cox, Johnson. Here's the automatic best fit, and here's specify. If you go to specify, you can select from the different distributions. And if you did actual distribution fitting, then you could use this specify distribution. Or if you have theoretical knowledge, like that it's a Weibull distribution, then you can use that. If you have no idea, you can just run automatic best fit. But what we'll do is we'll start with the Box-Cox transformation. And the Box-Cox transformation is very commonly used. And we have a few choices here. We have a rounded lambda. Basically, it rounds off that power transformation number to a common number like a 0 or a 0.5 or a 1. Optimal lambda will use the exact lambda value. And if you have negative numbers or 0, then you would need to select this lambda and threshold. We don't. These are all positive values. So we'll just go ahead and run the Box-Cox transformation. What we have now is, notice the different shape that this following the Box-Cox transformation. And this is the normal probability plot of the transformed data. The transformation that was used is a logarithmic transformation. So as you can see here, it's a ln, or a natural logarithm that is being used to transform the data. The process capability has gone up a little bit. It's 0.3. Now, I'm not suggesting for a moment that you use this technique to make your process capability numbers look better. It could have gone the other way. What you are doing, what's important is that you're trying to get to the truth. You're really trying to understand what is my actual performance. And you'll notice here the expected performance previously, we had 40%, now it's 17.6%. So this is a better assessment of the expected performance. The Anderson-Darling normality test is, in this case, for the transformed data, you can see that the data has been properly transformed. The data has been transformed to normal. Now, I do have one question. Isn't the Anderson-Darling test a lack of fit test? If so, it can only tell us that the data is not normal. It does not say that the data is normal, and I completely agree with that. In other words, if the P is low, you reject the null hypothesis, and that tells you that you have non-normal data. This 0.4 does not mean that I have proven the data to be normal. Okay, you're never actually proving normality. You can only basically prove non-normality. So keep that in mind. Just because your data says it's normal, it simply could mean that your sample size was too small and the test was not sensitive enough to detect that. Typically, if you get the Anderson-Darling p-value greater than 0.05, we'll make the assumption that the data is normal. All right, and thank you, Michael. It's a good point that you brought up. One of the things that's interesting here is that if you'll notice, if you look at the control chart, now the top chart is showing you the actual raw data, and then the middle chart is the individual's chart of the transformed data, and then this is the moving range of the transformed data. So you have the raw data, and the control limits are calculated from the inverse transformation, EXP, and the middle chart are basically the z-values, and so taking the logarithm of the data and control charting that. And what's interesting here is I want to point out is the fact that this process is actually a stable process, whereas if you looked at the original capability combination report, it appeared that it was an unstable process. So that's something that's interesting once you deal with this non-normality. Again, I'm not trying to torture the data until it confesses. I'm not trying to make the process look better. I'm not trying to say, well, you can improve your process capability by transforming. I simply want the truth of the matter, and the fact is that I had non-normal data, and the assumption, underlying assumption for process capability indices is that the distribution is normal. So you accommodate that by transforming, and now you have a process capability report that is more realistic. The next thing that I want to do is I want to run automatic best fit. So I'll go back to the data, and just to show you, the box cots work quite well, but what does the automatic best fit give us? So I'll rerun this, and this time I'll select automatic best fit. I'll put in my upper spec limit of 1,000, and then we'll run that. And what was selected was the log logistic, 2-parameter log logistic distribution. So actually the results are quite close to the results that we obtained from the Box-Cox transformation. According to our algorithm, is a slightly better fit. And actually, if you compare the Anderson-Darling value, lower is better. So that's a 0.24. And on the Box-Cox, we had 0.37. So it's actually a slightly better fit than the Box-Cox. Actually, you could have used either one. If you took the logarithm of the data, that's perfectly acceptable. Or if you run the best fit, log logistic, you see that it's the best fit, and that's the one that we're going to go with. In the distribution fitting, another tool that we have, because you may not be happy with just running the automatic best fit, you want to see, well, what are my other options? So I'll go back to sheet 1, and this time I'm going to run the distribution fitting, and that will show you everything. So I'm going to select all distributions, all transformations and distributions. And let me make that a little smaller so we can see it all. So there's our log logistic. And we have a lot of information here, so I'm not going to get into all the details. We don't have time to talk about the various measures. We talked about the Anderson-Darling. A lower number is better. And the p-values, of course, is the thing that we want to look at. What I want you to see is how, in descending order, notice how the line, the normal probability plot, the line is becoming less and less straight. So the fit is becoming worse and worse and worse until you basically get to the point where the distribution fits are really no longer valid, like largest extreme value and log and logistic and normal and so forth. Okay, but So it's a lot of information, but it tells you what will work and what won't work. You know, you come along here, and you can say, well, could I have used log normal? Well, yes, actually, you could have used log normal, or you could have used a box Cox. It just so happens that really the best fit in this case is the log logistic. Okay, so that's the all distributions and transformations. If I wanted to, let's say I wanted to specify a distribution, I could have actually gone back and run my process capability study here. I could have actually selected under specify distribution. I could specify, scroll down here, the log, that's logistic, the log logistic. Okay, and I could use that and then run the capability report that way. I won't do that because our best fit, automatic best fit, actually did that for us, but you can actually say what specific distribution you want. And just take a few moments to talk about the nonparametric methods. So now we're back to hypothesis testing. So remember, if I'm dealing with process capability or an individual's control chart, I do not have central limit theorem working for me, so transformation is appropriate. If my sample size is large enough and my skewness is small, in other words, it's just moderate non-normality, then the regular hypothesis tests will work. But if you have a situation where you have outliers or you have stronger skewness, then you need to consider these nonparametric tests. The one sample sign and one sample Wilcoxon are the nonparametric equivalent to the one sample T. Just a quick note on the difference. The one sample sign is more robust. The one sample Wilcoxon actually assumes symmetry, so I'm not particularly a fan of that one. It's a more powerful test, but it does assume symmetry, whereas the one sample sign is more robust, and so that would be the test I would recommend, and that's equivalent to the one sample T. The two sample Mann-Whitney is the nonparametric equivalent to a two sample T test, and then you have the Kruskal-Wallis and the Moods median test. These are nonparametric equivalents to ANOVA, where Moods median is considered to be more robust to outliers than Kruskal-Wallis. The runs test is also a nonparametric tool that you can use in conjunction with the run chart. And then if you're doing correlation, there is the Spearman rank correlation, which is a nonparametric equivalent to the Pearson correlation. So these are all different nonparametric tools that are in SigmaXL that give you robustness to the assumption of normality. To briefly discuss the nonparametric tests, they make fewer assumptions about the distribution. They don't rely on estimates of the mean and standard deviation. Rather, they use median and ranks. So they're sometimes referred to as distribution-free tests. But the nonparametric tests are not as powerful as the normal-based tests. That is the caveat here, is that you are losing power. However, if this, you are in a situation where you have non-normal data, sample sizes are small, and you don't have that central limit theorem that you can rely upon, then you pretty much need to look at the nonparametric tests. So with that, I'll switch gears and we'll look at an example. The examples that I have are from the workbook. We're using the customer data overall satisfaction. So I'm going to run a test of hypothesis on overall satisfaction by customer type. So typically I could do a one sample t-test, but in this case overall satisfaction is not normal, and so I want to do a nonparametric test. So I will do, let's say, a one sample sign test. The variable of interest is overall satisfaction. I'm going to stratify by customer type. So essentially I'm going to run 3 one sample sign tests. And the null hypothesis, in this case, we use the reference value of 3.5, but the null hypothesis is that the median is 3.5. When you're doing a normal-based test, the null hypothesis is typically you're working with the mean. Here, you're looking at the median. When I run that, here's the null hypothesis. The median is equal to 3.5, and the alternative, the median, is not equal to 3.5. And you can see that customer type 2, we reject the null hypothesis. So we can say that the median SAT score for customer type 2 is different from this reference value of 3.5, and in fact it's higher. The median value is 4.34. Let me just do one more, and I'll do a multiple comparison. And that one I'll use the Kruskal-Wallis, and the reason I like that is that we have a graphical view of the results as well. So let's go to the Kruskal-Wallis. Again, I'm going to do overall satisfaction by customer type. Now this time, this is similar to the ANOVA. In the ANOVA, the null hypothesis is that the means are equal. Here, the null hypothesis is that the medians are equal. In this case, we reject the null hypothesis, and you can look at the graph and you can compare. These are the confidence intervals on the medians for customer type 1, customer type 2, and customer type 3, and you can see that clearly customer type 2 has a higher median SAT score than customer types 1 and 3. So that's the end of my formal presentation. So what I want to do now is just scroll through, have a look at your questions. All right, so we have, what is the suggested method to determine future performance goals based on past data and having the bimodal distribution where the future opportunities for failure and the potential failures are not predictable? The metrics are service industry oriented, and what is measured are not widgets having an upper and lower specification limit. You know, in a case like that where your outcome is binary, pass-fail, then really then a proportion, and I should have mentioned that at the outset, that all these transformations and distribution fitting are applying to continuous data, not discrete data. So if you simply have a pass-fail outcome, then really what you can do is you can apply proportion, but you can also add a confidence interval. And in SigmaXL, we have a one proportion calculator. You can plug in the proportion, and it'll give you the confidence interval. And there's also a sigma level calculator if you want to use that to get a sigma level with discrete data. Not really, the question of normality doesn't really apply here. It's simply you have pass, you have fail, what's my proportion? So I would use the one proportion calculator and get the confidence intervals, and that's what you can use to report process performance in that case. Ashok asked the question, for continuous non-normal data with a heavy skew, what is preferred, transformation or nonparametrics? You know, again, it depends on what you're doing. If you're doing hypothesis testing, it's a lot easier using nonparametric tests. You can try transforming, but then you get into the situation where if I'm doing a two-sample t-test, I have to apply the transformation to both samples, and you could go that route, but really you're much better off, if you're doing hypothesis testing, stick with the nonparametric tests. On the other hand, if you're doing process capability and or individual control charts, then transformation should be used. And okay, Michael asked about the fat pencil test for normality. All right, what that is George Box, the eminent statistician George Box, said, all right, you want to know how to read a normal probability plot? Just take a fat pencil and lay it on your normal probability plot, and if the fat pencil covers the data, then you have normal distribution. So, and essentially, that's the idea of these confidence intervals, is to give you kind of a visual picture. But here's a situation where the fat pencil would help. You're never going to have a perfectly straight line. So the fat pencil test by George Box says just that. You obviously you have to print the graph out, or you put it on your screen and with a fat pencil, and if it covers the data, we have the confidence intervals, so you can pretty well eyeball the fat pencil. Let's call it end of presentation. So thank you all very, very much.